All right, in this lesson we have two objectives. So for any arithmetic sequence, we want to find the nth term when n is given, and n when the nth term is given. And given any two terms, find the common difference and construct the sequence. And then our second objective is find the sum of the first n terms of an arithmetic sequence. So a sequence is arithmetic if there exists a number d called the common difference such that a sub n plus 1 is equal to a sub n plus d for all n greater than or equal to 1. If we solve that equation for d, it says that a sub n plus 1 minus a sub n is equal to d. And remember from the previous section, this means that the arithmetic is happening in the subscript. So the n plus 1 tells us it is the term after a sub n. So to find the common difference, we subtract any term from the term that comes after it. So let's do an example. So we have find the common difference of the sequence 6, 11, 16, 21, and 26. So we have our A1, A2, A3, A4, and A5. So in this case, it says to find D, we subtract any term from the term that came before it. So the term before A2 is A1. So A2 minus A1 is 11 minus 6, which gives us 5. But notice if we do A3 minus A2, that is 16 minus 11, which is also 5. And A4 minus A3 is going to be 21 take away 16, which is also 5, and so forth and so forth. So that is what it means to be an arithmetic sequence. So what that tells us is, well, what is the difference between each of these terms? So to go from 6 to 11, what did we have to add? Oh, well, that was the number 5, and that is our common difference. All right, so the general term, or the function that represents a sequence, is given by the following. So the general term of an arithmetic sequence is given by a sub n is equal to a1 plus n minus 1 times d, where a1 is the first term of the sequence and d is the common difference. So we can use this to find the general term of a sequence. So note, if you watched the video earlier for 11.1, we did this, but we did it by just reasoning through and looking for a pattern. Whereas this formula will give us a way to find it algebraically if we know some certain information. So for our sequence 3, 10, 17, and 24, we want to find the following. The 1001st term of the sequence, and we want to know, well, what term is 19,113? So starting with our formula, we have a sub n is equal to a1 plus n minus 1 times d. So we need to figure out some of these things. So the easy one is going to be, well, the first term of the sequence, that's the first thing in the list, so that's going to correspond to the number 3. And now we need our common difference d. And as we just did in the previous example, we know that we can find d by subtracting any term from the term that comes after it. So for instance, we would have 10 take away 3 would give us d is equal to 7. So now that we have n and d, we put them into our equation, and we get that an is equal to 3 plus n minus 1 times our d, which is 7. And we can simplify this up a bit by distributing into our parentheses. And we get an is equal to 3 plus 7n minus 7. So a sub n is equal to 7n take away 4. So now we're ready to answer the question. So it wants we want to know, well, what is the 1001st term of this sequence? Well, we're going to use n equals 1001. We put that in, so a sub 1001 is 7 times 1001 take away 4, which is 7007 take away 4, so we get that it is 7003. All right, so the second part of this example says, well, what term is 19,113? So this time we were given the output and we were asked to find the corresponding input. So what we really want is we want the input n when a sub n equals 19,113. So this is like when we're given a y value for a function and asked to find the x that gave us that y value. So that would give us the equation 19,113 is equal to 7n take away 4. So we add 4, and that gives us 19,117 is equal to 7n. And then we divide by 7n, and we get n is equal to, so 19,117 divided by 7 gives us 2,731. All right, let's take a look at our next example. So example 3 says, find the general term of the arithmetic sequence if a sub 3 equals 2 and a sub 7 equals to negative 14. So how is this different from the examples we've been doing before? Well, in all the previous examples, we were given the sequence as a list, so A1, A2, A3, A4, and all of the terms were next to each other in the sequence. Well, this time, we were given the third term, and we were given the seventh term. All right, well, let's write down what we know. We don't know A1, we don't know A2, we do know A3, which is 2. A4 we don't know, A5 we don't know, A6 we don't know, A7 we do know is negative 14. So if we use the definition of an arithmetic sequence, and remember our definition for an arithmetic sequence says that a sequence is arithmetic if there exists a number d called the common difference, such that to get to the next term, so the next term is an plus 1, we have to add d to the term that came before it. Well, if we start at 2, which is the third term, to get to the fourth term, we would have to add d. So we would have 2 plus d. But then to go from the fourth term to the fifth term, we would have to add another d. So we would have 2 plus d, but then we would need another d, so plus d, and that would give us 2 plus 2d. And then to get to the next term, we would have 2 plus 2d, but we would need to add to it another d, and that's going to give us 2 plus 3d. And then finally, to get to the next term, we would have to add another d. So 2 plus 3d plus another d is going to be 2 plus 3d plus d, and that's going to give us 2d, or 2 plus 4d. So then these two things would have to be the same. So that tells us then that 2 plus 4d has to equal to negative 14. So we minus 2, and we get 4d equals negative 16. Divide by 4, and we get d is equal to negative 4. So now that we know d, we need to know the first term to find the general term of the sequence. So we know to move forward, as we saw here, we had to add d every single time to get to the next term. Well, to go backwards then, we would need to subtract d, so 2 minus d, and then this would be 2 minus 2d. So a1 is equal to 2 minus 2d, but we just found that d is negative 4. So 2 minus 2 times negative 4 is going to give us 2 plus 8 is equal to 10. So now, if we know a1 and we know d, we can use our formula. So an is equal to a1 plus n minus 1 times d. So a sub n is equal to 10 plus n minus 1 times a negative 4. Distributing in to open up our parentheses, we end up with a sub n equals 10 minus 4n plus 4. So a sub n is equal to negative 4n plus 14. And that would be the general term of our sequence. So let's go back and look at what we did and see if we can find a more economical way to resolve this. So we'll notice we were given the third term and the seventh term. So we could write out how many d's it took. We added d, we added d, we added d, we added d again, a total of 4 times. And in this example, it wasn't too bad because we only had to go from the third term to the seventh term. But if I was given the 5th term and the 100th term, I wouldn't really want to make a list with 100 things in it. So what we notice is the following, that the number of d's added is the same as the difference in the position of the sequence members. We can use this to make the process much more efficient. So what we notice then is that if we had a sub 3 is equal to 2 and a sub 7 is equal to negative 14, we have that a sub 7 is equal to a sub 3 plus 7 take away 3 times d, where we have our 7 and our 3. So we then know the values of a3 and a7 as they were given. So then this results in the following equation. Negative 14 is equal to 2 plus 4d. And we'll notice this is exactly the equation we got in the 7th row up here when we did this. So now this would allow us to solve for d. So the key idea here was that the number of d's added is the same as the difference in their position, which is 4. So 7 take away 3 gives us 4. So going from the third term to the 7th term required us to add 4 d's, and that will allow us to solve this equation. So as we did above, if we minus 2 and then divide by 4, we ended up with d is equal to negative 4. So then we could use the same thing to help us determine what a1 was. So using our general form of the equation, we have a3 is equal to a1 plus 3 minus 1 times d, where a1 is what we want. We need the first term. And we know the rest of these because we've either solved for them or they were given. So a sub 3 was 2, A1 is what we wanted. 3 minus 1 is 2, and D was negative 4. So 2 equals A1, take away 8, and we add 8, we add 8, and we get 10 is equal to A1. So putting all of that back together in our formula, we have AN is equal to A1 plus n minus 1 times D. So AN is equal to 10 plus n minus 1 times negative 4. And we are back to where we were the first time. All right, so now we want to talk a little bit about Gauss's method. So Gauss's method is a way to add up the terms in an arithmetic sequence. So as the story goes, this method was used by Gauss when he was a young child in grade school. He got in trouble and they sent him to the corner to wear the dunce hat. And he was told that he couldn't come out until he had added up all of the numbers between 1 and 100. So, as the story goes, he was sent to the corner. He was there for a few minutes and then says 5,050, which turns out to be the sum of the numbers from 1 to 100. So the question is, well then how did he do this? Well, here's the idea. So say we're trying to add up the numbers from 1 to 100, so that's S100 would be 1 plus 2 plus 3 plus all the way out to 98 plus 99 plus 100. So the first observation that Gauss made is that if you change the order that you add things in, it doesn't matter. So if we write this list in the reverse order, so 100 plus 99 plus 98 plus all the way down plus 3 plus 2 plus 1, that doesn't change what the sum is. Then, if we were to add these two things together, we'll notice for each of these pairings, so I have 1 plus 100, which is 101, plus my next pair is 2 plus 99, which is also 101. And then if I look at my next pair, I would have 3 plus 98, which is 101, plus all the way out. In fact, what would all of these pairs give us? 101 plus 101 plus 101. So now, how many 101s are there in this list? Well, there are 100 101s in this sum. But adding the same thing again and again is the same as multiplication. So repeated addition is multiplication. So then this is 1001 times 100. But that's not quite the original answer we were looking for, because it was the sum we were looking for plus the sum we were looking for. So it's too big. We counted it twice. So to fix that, we divide by 2 because we double counted everything. So then 2 goes into 150 times, and we have 101 times 50, which is 5,050. So the sum of the first n terms of an arithmetic sequence is given by this formula, which is a generalization of the example that we just did. So we have that S sub n is equal to n times a1 plus an divided by 2. Well, that's exactly what we had here in this formula. So our first term plus our last term times how many things there were, and then we had to divide by 2 because it double counted everything. So this is really just that formula in general. So let's double check. So S sub 100 would be n, which is 100 things, times 1 plus 100, all divided by 2, and it reduces to the same thing, 5,050. Well, let's double check that. So if we were to write out 1 plus 2 plus 3 as an arithmetic sequence, we would have our first term is 1 plus n minus 1 times d. Well, our d in this case is we're adding 1 to get to the next term every time. So then this is going to be 1 plus n minus 1, which just gives us n. So the general term of our sequence is just n. And then we would start at n equals 1, and we're going to stop when n equals 100. So in sigma notation, we would have the sum as n goes from 1 to, wow, not infinity. We're stopping at 100. We'll talk about infinity later, of n. Well, let's check this on our calculator. So to do the sigma notation on our calculator, remember we press alpha and then window and choose choice number 2 for our sigma. And then we have n goes from 1 to 100 of just n. We press enter and our calculator thinks for a minute and it agrees with the values that we were getting out of Gauss's formula. So either way we calculate that sum, we get 5,050. So you're probably thinking, well then why the heck do we need this formula if we can just put this stuff in our calculator? All right, well let's go ahead and give this next guy a try. So find the sum 1 plus 3 plus 5 plus dot 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 999. So 999,997 plus 990,999. So we do the same thing. We need to find our a sub n. So our first term is 1 plus n minus 1 times d. And our common difference is going to be, well, to go from 1 to 3, we had to add 2. So times 2. If we multiply this out, we get 1 plus 2n minus 2. So that's 2n minus 1. So now we need our starting value and our stopping value. So our first term is 1, and then we have 2n minus 1, and our stopping term is 999,999 equals 2n minus 1. So we add 1, we add 1, we get 2 equals 2n, divide by 2, divide by 2. So that tells us that we start when n equals to 1, and we're going to stop when, so we add 1 to both sides, and we get 1,000,000. And 2n, we divide by 2, divide by 2, and so we stop at 500,000 is equal to n. So then in sigma notation, we get our sum as n goes from 1 to 500,000 of 2n take away 1. We're like, all right, let's put this in our calculator. So alpha window, and we get choice number 2 for our sum, and we have n goes from 1 to 500,000 of 2n take away 1. We press enter, and we wait, and we wait. Turns out, no matter how long we wait, this is never going to terminate. We'll notice over here on the right side, our TI is thinking. So if we ever get our calculator caught in essentially an infinite loop, to make it stop, we press second and our on key, and it's going to say break, and we say, yep, quit, and then it's going to give us an error. So for this problem, we would be unable to find the sum using our graphing device. So we're going to have to use Gauss's formula. So we now have all we need. So we have S sub n is equal to n times a1 plus an all over 2. Well, luckily, we already solved for what our n is. And then we know our first term and our last term. So we're going to have 500,000 times our first term was 1, and our last term was 999,999. And then we divide all of this by 2. So that gives us 500,000 times 1,000,000 over 2. And this we can put into our calculator. So 500,000 times 1,000,000 all over 2. And we get 2.5 e to the 11. And in case we don't remember, what does that e to the 11 mean on our graphing calculator? So this tells us that it is in scientific notation. So the e to the 11 means times 10 to the 11th power. So in other words, we need to move the decimal to the right 11 places. So that's going to be 2500. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So then we would get this as our number, so 250